Okay, welcome back. Today I'd like to talk about a pretty famous inequality known as the Jensen's inequality. Basically what it says is, given a real random variable x here, and a convex function f, then expectation of fx will be bigger than equal to f expectation x. By the way, the convex function is supposed to be some shape like that. Of course, this makes sense only when f is kind of mapped to a real number. It's a convex function, it should be real also. It can be n dimensions, something like that. And then in the sense that x should be a real random variable, as I state here, I think like I write this in another form, a little bit more general, that even though this one is much more common, I can also write like expectation f gx is bigger than equal to f expectation gx. And again, I have like f is a convex function, and g is an arbitrary function here, and makes a random variable. Of course, if I have this, it immediately implies that. So before I try to argue like why this is true, I'll just give a use of this inequality here. So let's try to show that using this inequality that the KL divergence is non-negative, and remind you that the KL divergence of, or like we're using like notation using D here, or the relative entropy between P and Q is defined as like Px log Px over Qx, like that. And then now I can write this as Px x minus log, minus log Px over Qx. Now what we can see here is now minus log is f, can be think of a function f that is convex, and Px over Qx is like gx here. And now we are basically doing expectation. This is basically expectation of minus log Px over Qx. And from the inequality here, we know that this is bigger than equal to minus log expectation. I'm sorry, of course I flipped the sign here. I forgot to change this. Put the negative sign here. I forgot to flip the denominator and numerator. So this will be Q over P. This will be Q over P also. And then like it will be expectation Qx over Px. And this should be equal to, okay, some x Px Qx over Px. So Px got cancelled. I'm saying Qx here is a PMF, a probability mass function. These terms will sum up to 1. So therefore this minus log thing here will get to 0. So again, we show it differently last time. actually, or maybe like some videos before that, like the K divergence should be bigger than equal to 0 using an inequality that something like minus log x is bigger than equal to x minus 1, but here we use the Jensen's inequality to show this instead. Okay, let's see how we can show this expression here, the inequality. Let me expand this into this form, these two, the both left-hand side and right-hand side, into this form here. And okay, here I'm assuming that x is discrete, but actually this is also true. I mean, this expression is actually also true when x is continuous. But I am not going to prove that more general case here. And I also basically I won't give the whole proof for the discrete case also, but I will give the key step. Basically, this can be shown, the inequality can be shown using induction. And let's consider the simplest case, when not exactly simplest non-trivial case, when x can only take two outcomes. Let's say x can either be x0 or x1. And so then I basically have something like this. I have this is the convex f function, and let's say this is gx0 and this is gx1. And I can draw a line here, so it's about this point here. Okay, let's keep this like this first. And since I have only 2 points, I can just write this expression as p x0 f gx0 plus p x1 f gx1. Oops. And this is f px0 gx0 plus px1 gx1. And now let's look at this left-hand side here. Fgx0 is basically this point here, right? Or I should say the height of this point here. This is Fgx0. And Fgx1 is the height here. And since Px is basically a PMF, probability mass function, Px0 and plus Px1 should be equal to 1, and Px0 and Px1 should both bigger than equal to 0. So as we vary Px0, basically I have a line draw between these 2 points here, and this expression on the left hand side is basically the height of a point fall on this line, right? For example, if Px0 is equal to 0.5 here, basically this expression here on the left hand side is just the height of this point here. So therefore left hand side is, okay, this may not be, this is the left hand side. So how about the right hand side? Right hand side is very similar, right? Basically I have this f of this px0 g px0 plus ps1 gx1 is basically, this expression is just this point here, I mean on the x-axis is just this is px0 gx0 plus px1 gx1. So therefore the f of this guy here, that's the right hand side here, is just this height here. So now you can easily see that like why we have the Jensen's inequality from this specific case. Apparently, we'll have this left hand side is always bigger than equal to right hand side. Moreover, we can claim that this left hand side is exactly equal to the right hand side, only lie at the two endpoints. At the two endpoints is basically when px0 is equal to 0 or equal to 1. So basically, that x is deterministic. Okay, let me quickly complete this proof using induction here. So we will first assume that like x is true. The Jensen's inequality is true when x can take n-1 different values. Let's say x0, x1 up to xn-1. Then we want to use this fact or this assumption to show that Jensen inequalities will still hold when we assume that x can take n different values from x0 up to xn, let's say. And this I just wrote the expression for the case when x take n-1 different values and when x take n different values. So if I look at the left hand side of this guy here, that x take n different values, I can expand that, just basically pull out the first n-1 terms and just move the last term outside. Now I compare this guy with the assumption here, so they are more or less the same. It's very tempting to just use this inequality here, but note that I cannot use it directly because here pxi is a PMF, therefore should sum up to 1. This, strictly speaking, is not exactly a PMF because it doesn't sum up to 1. Instead, it should sum up to 1 minus pxn, because px for this one, when we sum from 1 to n, pxn basically is a PMF here, therefore should be equal to 1. Therefore, summing from 1 to n-1, summing pxi from 1 to n-1, we should get 1 minus pxn. So, okay, but in any case, therefore I can simply scale this guy, right? So I can scale this pxi here into pxi over 1 minus pxn. And basically I pull the same expression outside here. Now I can use this inequality here now because now this guy is a valid PMF that is sum up to 1. So this is a valid PMF. So therefore I can use this inequality here. So I just have this expression here is bigger than equal to this expression here. And then I can use what we have shown earlier for this expression here. And again, we have two terms here. Now this px0 becomes 1 minus pxn, and ps1 up there becomes pxn here. Now if I use this inequality, I will get this. And basically I can get this 1 minus pxn get cancelled, and you can see this is just equal to I didn't have any I can just write it down as this expression here, or I can just copy it here, I guess, if this is just equal to that. This shown the Jensen's inequality for the case when x takes n values, and therefore by induction, Jensen's inequality will hold for x takes any number of values. So therefore, like, we kind of show that like it's true for any discrete x. One last thing I want to point out is that for the Jensen's inequality, this inequality will become equalities only when this x is deterministic, or in other words, pxi is equal to 1 for one of these I and equal to 0 for the rest. Actually, you can easily see that, like, if you go through this proof more carefully. Basically, if you think of the induction for a particular n, let's say n equal to 10, is if you can think of it basically using this inequality like 10 times, and because we showed it earlier that this inequality, actually we argued that earlier that this inequality holds only when like x is deterministic in this case, and this property will just propagate each time you use this inequality. So anyway, if you're interested, just reread this. I guess like you will be able to convince yourself that this property is true indeed, that Jensen's inequality will become equality only when x is deterministic. Okay, and that's all for me for Jensen's inequality.